So I'm going to introduce my simulation project today. So the first thing you have to do is go to the website and download the actual project. There's a big downloads button on the top right here. Click it and you're going to want to download the simulation.zip file. Now I've already done this, so I'm just going to go ahead and go to it. And I downloaded it right there. It's a little tough to see, and I've extracted it into this simulation folder. So just going to double click and open that up, and you can see there's this simulation.jar in the root level. So just double click that, and the first thing you're going to see is basically just a quick welcome screen that asks you for a couple input parameters. As you can see, the UI here wasn't really the main concern. So one of the options is which geographic area do you want to look at. These are actually just KML files that are being loaded directly from the geo areas folder, and so if you want to, you can very easily drop another KML file in there, and we'll show you how to do that later. And then you can choose the quote real network of the system, and so right now there's not a very descriptive naming convention, but we'll just stick with network 1 for now. Tendency to move basically describes the users in the system's tendency to move within a single heartbeat of the simulation. And so sometimes users move, sometimes they don't move. And so 1 indicates that everyone will move every heartbeat, and 0 would indicate that no one would move. I've grayed out mobility in meters due to a complication with translating the meters to pixels, but essentially this would dictate how much people moved. Then you have the time per heartbeat. So for each heartbeat of the simulation, how much time does that equal in real time? And what this allows you to do is figure out how many, quote, real days the simulation is showing you. The input frequency determines how often users send updates to the network. So sometimes they'll send them, if they send them every single time they move, then you'd get a 1.0 value here. If they never send updates to the network, then you'd put a 0, and then all the percentages in between. And then locational accuracy allows you to choose whether the locational accuracy is GPS or network accuracy. So hopefully at some point we could do that on a per individual basis, but right now I just have it across the board. All users in the simulation are operating at GPS locational accuracy. So let's go ahead and start it, and it'll take a second to get started here. It does quite a bit right when it's starting up. One of the big things it does is for each of these, each of the polygons in the loaded KML file, it has to do a latitude-longitude conversion, and that takes a pretty substantial amount of time. So just to introduce you to what we're seeing, so basically we're seeing some users, which are represented as small green dots, moving around, and as they move around, they put in values to the simulation manager, and it is actually updating the perceived map of the network. So if we zoom in here, you'll be able to see, let's zoom in right here where it's a little bit dark, and you'll see as the green dots move around, you'll see that the network is being updated in the locations that the green dots are moving to. So I'll just let you observe that for a moment. Just look at the black areas. There we go, and we can see that they're slowly eating away at all those black areas. So what we're looking at here, we're looking at basically a perceived network, and the network is just fake. I've just created a fake network topology, and if we want to see that, up here in the top right, it tells us we're viewing or top left, we're viewing the perceived network. Press R to change. R stands for let's look at the real network. So I'm going to go ahead and press R, and you see we've now switched to the quote real network of the system. There is a color scheme difference, but the relative differences of the images are the same. So I'm going to press P to switch back to the perceived, and you can see that it does look very much like the real network. So we're going to do that a few times. Alright, so some of the metrics you have in the top left, it tells you the frame rate it's operating at, the number of heartbeats, aka the number of full updates in the system, the simulation time. We have this slowdown factor, which I'm actually slowing the simulation down so you can see it. If I press plus, you'll notice that the slowdown factor in the top right starts getting smaller and smaller, meaning the simulation is running faster and faster. So I'm just going to go ahead and bump it down to as fast as we can run, and hopefully the video frame rate is high enough that you'll be able to tell that these dots are moving substantially faster and the network seems to be conforming much faster. down below the slowdown factor, I have my overall metrics, which are basically the output metrics of my system. You'll notice that right now they're all just represented as XX percentage, XX percentage, XX percentage. And the reason for that is basically it's right now I have no continuous algorithm to calculate these metrics, and the calculation is very, very expensive. I'm essentially brute forcing and comparing every pixel of the real network to every pixel of the perceived network. And as you can probably tell from the simulation, the perceived network is being updated every single frame. And that makes it really, really tough to calculate the coverage of the amount of coverage that the perceived network shows, the accuracy of that coverage relative to the real network, and the total accuracy while you're actually viewing the simulation. So I've got code to do that offline, but doing it online basically slows the entire thing down to a crawl. So that would have to be a future enhancement for the system. So some of the limitations of my system here, you might notice, if you watch this long enough, you might notice that around the edges of the simulation, there's basically just an empty area where there are not very many smartphone users wandering around. And the reason for that is that when users exit the topology of the network that we're looking at, they basically get ejected from the simulation. And currently there's no influx of users back into the simulation, resulting in a net, basically a net loss of users over time. So that's one of the limitations that I'd like to address in the future. So some of the features, you saw some of the various inputs that we have. We've talked before about the OO design and how stuff like the moving strategy, that each user has their own individual moving strategy, will allow us to map this construct that I've created to to a real system. In the time allotted, I haven't really had a lot of time to look up how do people actually move. So when I do have time to look that up, I can hopefully actually represent it in my simulation with very little additional work. Some of the other features, so I've got this so it generically loads in geographical areas. So let's say we want to look at West Virginia, and instead of network 1, we're going to look at network 4. Sure. And just to show you that these parameters work, let me slow down the tendency to move to 0.1, which means that only 10% of the time will someone actually move. And so again, it's going to take a while to start up. And so now we're looking at West Virginia. You'll notice it looks a little funky, and the reason for that is that I'm using a Cartesian projection of latitude, longitude to pixel coordinates. And Cartesian projection is only really useful for a very small latitude, longitude area. And the area which I'm doing right here is much too fast, or is much too wide to be accurately represented with a Cartesian projection. So we're getting a lot of stretching and skewing in the map. So you can hopefully tell that these users are not moving nearly as fast as they were the last time. So what I'm going to do is go ahead and hit the plus and speed up the simulation, so that even though they're not moving quite as fast, the simulation is going faster, so it looks like they're moving fast enough. Okay, so it looks like we're seeing a perceived network that's some bars. So I'm going to hit R and switch to the real network. And we can, again, there's a color scheme difference, but we do see that there are some horizontal or some diagonal bars going on here. And switching back to the perceived network again, and you see the same bars. The reason that the color scheme difference is there is right now, in order to generate the perceived network, one of the implementation details is that I have to go through a grayscale translation. And so when I go from this real network, which has tons and tons of colors, to a grayscale translation, they get flattened to 256 colors. And then I'm actually restoring those to 256 colors that I've chosen. But unfortunately, the color mapping almost never works out perfectly when you go from millions of colors to 256 colors. So that's why we end up seeing these bars. It's probably difficult to see in the video, but if you actually look closely at the real network, the bars, the diagonal bars that we're seeing here, actually correspond to different shades of lightness or darkness in the real network. So I don't know if you can see this really dark diagonal bar here and the really light one up at the top that actually correlates fairly well in the Perceive network. So some of the implementation details, zooming. I can perform zooming as easily as I want to. The problem is it takes a while. So when we're looking at KML, like this county of West Virginia, we might be looking at 100 or 200,000 points in the KML, and therefore zooming takes a significant amount of time in order to translate all of those latitude, longitude pixels into the new zoomed array. And so one thing that hopefully we could do is if I could use a proper projection library, then it might have some optimized code that can do that significantly faster. Unfortunately, I couldn't get any of those working, and so I ended up just rolling my own. A secondary limitation of this system is that it uses quite a bit of memory, and it doesn't do so very well. It tends to thrash the memory, and it could probably run quite a bit faster if it didn't do that. Again, that was just it was an optimization, and something that needs to be done at the end of development rather than the beginning. So let me check over my list here. All right, so if we want to look at these network images, it's actually, if you wanted to implement more, quote, real networks, you just drop any image into this network images folder, and you can just, looking at my images, you can see they're just any sort of image that you would like, and they will actually be stretched to fit the size of whatever screen you're running on, and their color schemes will be corrected to match the internal color scheme of the system. Again, there will still be that color scheme difference, but hopefully at some point I could deal with that. If you wanted to implement more geographical areas, so I've already showed you Virginia, counties, and West Virginia, and so let's say we want to look at Alabama real quick, and we'll look at we'll say network 3, and yeah, we'll just leave everything else alone. So this is Alabama. This is the counties in Alabama. And if I speed this up so that it conforms quite a bit faster, you'll start to see that it looks a lot like the real network. So there's the real network, and here's the perceived one. So, yeah, so if you wanted to implement more, I'm going to press escape and get out of this. If you wanted to implement more counties, you have to actually, so you can just download them straight from the census website, which I have right here, and right there is the URL. You need to download the shape files, the SHP files, and then unfortunately I couldn't get shape working, and so I ended up converting shape files to KML. None of the, basically the shape file was just significantly more complicated than anything I had ever done with geographical systems. So I was familiar with KML, so I kind of went with that route. I'm sure somebody could get it working with shapefiles, but I couldn't do it. So the way that you do that is you essentially choose whichever shapefile you want. It's pretty easy. You just search for the census and then search for census shapefiles. You download whichever one you want, and then you use this program called Shape to KML in order to convert the shapefile to a KML file. And that program is actually not available for free online anymore. I went ahead and put it on the download section right here, KML Converter. It was basically the #1 program that everybody used, but it got outdated and people stopped publishing it because it was just outdated. And so I managed to find the source, and I downloaded the source and made some of the modifications needed to upgrade it to more modern Java. And so I was able to get that running, and it's just available as a zip right there. So you just have to download that and use that to convert the shape to KML. And after you have a KML file, you just drop it right into the geo areas folder, and the simulation.jar will just pick up on it and allow you to load it. So yeah, so that's my simulation. So I hope you like it, and let me know if you have any questions. All right.